Hi everyone, in this video I'll be going over the solutions to problems from the weekly contest 246 of Leetcode. So yeah, let's just get right into the first problem. I will provide timestamps to any problem if you just want to find that one uh, in the video player, so you can skip to any problem to see the solution. Yeah, so without further ado, let's get into explaining the first problem. So in this problem you're given a string and you want to find the largest odd number that is present inside of this string. So uh, in 52, 52 is even, but a sub number in 52 is 5, and that's odd. So in this problem, you just need to come up with one realization. It's that the only thing that determines if a number is odd is the last digit. So it doesn't matter what these numbers are. If the last digit is odd, then everything before it will be, it doesn't matter. This entire number here will be an odd number. And so with that in mind, since we want to find the largest odd number, we simply just need to find the last occurrence of an odd number inside of the string. Because if we have like a number like 1, 4, 9, 3, the last odd number inside of the string would be 3. So we would want to grab all of this. And let's say we had an even number after it, then 3 would still be the last occurrence. And this is simply just because we have the most stuff in front of it, and the more stuff you have in front of it, the larger the number will be. So this simple realization will allow us to find the largest odd number present inside the string. So let's just take a look at how that's implemented. We'll have an index representing the last occurrence of an odd number. Then we'll loop over all of the characters inside of our string. This converts it to an integer because since this is a character, we'll want to subtract the assay value of 0 from it. So what this line of code does is it'll turn a character, let's just say 9, into an integer of 9. So yeah, so this will convert the character to an integer. We check if it is odd. If it is odd, we will set our last variable equal to that index. So now we know the last index of which there's an odd number. So in this example, 0, 1, 2, 3, 4, those are the indexes. Our last variable will be set to 3 because 3 is the index of the last odd number in string. Now we simply need to return the substring of that. Because substring goes exclusive to the endpoint, we'll want to substring from 0 to 4 because that will go from 0 all the way up to 4, but not including 4. So we'll grab 0, 1, 2, and 3, exactly the string that we want. So yeah, that is the solution for largest odd number in string, and it gets accepted as you can see here. Alright, now let's look at the second problem, the number of full rounds you have played. So in this problem, you are given a start time and a finish time that look like this. And there are rounds in this game that occur on 15-minute intervals. So a round occurs at the start of an hour, 15 minutes into an hour, 30 minutes into an hour, and 45 minutes into an hour. You are supposed to return how many rounds a player has played given a start time and a finish time. And in their example, we can see more clearly how this game works. So if we start at 12:01 and finish at 12:44, we know we cannot join this round because it already started. So we will round up to the next starting time of the next round. So that's at the 15th minute of the hour. So we will play one full round from 12:15 to 12:30. Then we know because we finished at 12:44, there's no way we could have played the round from 12:30 to 12:45. And then same with explaining this. So yeah, now let's just get into the solution. So the first thing we need to do is we notice that um, the start time and finish time, they can essentially be rounded to the nearest like round start or end. So we want to round start time up. What I mean by that is if start time has, it doesn't matter what this hour is, if start time occurs at like 03, we'll want to round this up to 1:15 because that is the first round that that they could have played in. Using the opposite logic, we'll want to round end time down. So if we end at 1:44, like their example, we'll want to round that down to 1:30 because the that's when their final round will end. So now what we know is we can we know that when they start at 1:15 and 1:30, that's the same thing as starting at 1:03 and 1:44. Because when you start at 1:03 and 1:44, you'll only be able to play the round from 15 to 30. So these two start and end times are equivalent. So yeah, so the first step is to just round these. Next, we can just perform some math to figure out how many rounds will go by. We can take the end time, the end minutes, and subtract the starting minutes and divide that by 15 to figure out how many rounds will go by with the minutes. So in this case, 30 minus 15 divided by 15, that's just one round. So that's one. And so now we can do some math with the hour marker. So let's just say we started at, let's just say we end at, let's say 3:30, right? So using this minutes calculation, we will find that one round will pass in the minutes. Next, we can perform the calculation with the hour. So we can just subtract the final hour from the start hour from the final hour and multiply that by 4 because there will be 4 rounds played every hour. This will give us how many rounds will be played in this time span between the hours. So this will give us 8. So the answer for this test case here, starting at 1:15 and ending at 3:30, would be there are 9 full rounds played. So yeah, there's only one more case we need to think about, and it's that start time can be ahead of finish time. So in this example of their test case here, when you start at the 20th hour and finish at the 6th hour, you will have to carry over to the next day. So you will play 16 rounds from 20 to 0 because since this is a 24-hour clock system, you'll go from 20 to 24 hours, and that's 4 hours times 4 rounds an hour. That's 16 rounds. And now you will start over from the new day. So you'll start from 0, 0, and then go to the 6th hour of the day. So we can account for this test case just by simply pretending. We can just do this sort of calculation here twice. We can just pretend that our end time is the 24th hour, perform a calculation, then move our start time to 0 and our end time as this, perform another calculation, and sum those rounds together. So in this example, we'll have 6 hours times 4 inside of this, and then we can just sum these two answers we calculated for these two different cases together, and that will give us 40 full rounds played, starting from hour 20 and carrying over to hour 6. We can just do this by breaking it up. by setting one endpoint to 24, then moving the start point to 0 and using the endpoint of 6. One more thing to note is that this strategy of calculating the minutes and this strategy of calculating the minutes and hour to figure out how many rounds will be played works with negative number cases as well. So if we imagine a case like this, 145 and 330, then with our minute calculations, we will have something that looks like this. The final minute minus the original minute divided by 15. This will equal -1. And when we do the hour calculations, we'll get 8 again. When we sum these up, this will equal 7. And as you can see, this logic still works. 7 is the correct answer here. You can think about this like so. We will skip from 330, we will skip from 145, sorry, since this is the start time. We will skip from 145 directly to 345. There will be 8 rounds played between 145 and 345. Then we need to backtrack 1 round by moving from the 45 to the 30. So we know we need to subtract a round from 8, which gives us our final answer of 7. There are 7 rounds played between 145 and 330. So yeah, this is just to prove that this strategy will work even when the numbers are negative inside of this minutes thing, because instead of adding an extra round, we'll just be subtracting a round, because we'll go from 145 to 345, then subtract 1 round because we want to end at 330, not 345. So now let's take a look at how that's implemented. My code for this is quite messy. I was just using, since this is in the contest, I was just coding up the quickest solution that I think would work, and I didn't want to spend too much time just thinking about it, so I was just typing really fast and trying to get a solution out. So I have this time class, and this will essentially parse a string into a minute and hour variable that it will store as a field. So this just finds the index of the colon and breaks it into 2 integers around that colon. So this is a fairly straightforward part. And this code here is irrelevant since my first solution TLE'd, because I didn't do this math here to quickly figure out the answer. I was just looping through the time. So yeah, we don't need this code here. Whoops, sorry about that. Yeah, we don't need this code here. So this is all the time class needs to do. So now we can look at our actual class, which is kind of a mess. But we will create 2 new time objects given the time, start time and finish time. Then we will round start time up and finish time down. This is what this massive if-else string of statements will do. Essentially what it does is it checks all these 4 intervals, right? So if start time is if start time is in a minute where it's like 1:04, it'll round start time up to 1:15. Since 1:15, we know that will be the earliest round that is possible to start. And similarly, it'll check the bucket for when start time is between 1:15 and 1:30. So if we start at 1:16 or 1:29, both of these will get rounded up to 1:30. And similarly with the ending times. And the starting time, the only thing you need to worry about is when you're rounding like 1:46 up to the next hour, you don't want to have 1:60. Of course, you want 2:00, which is just a simple if. Since we have already an if check for this bucket, we just need to have slightly different logic for here. And the same thing goes for the end times. We'll want to round everything down instead of up. So that's what this does. I think it's fairly simple to understand, so I won't be going over every single check, but I will be providing source code in the description. So yeah, and now here is where we perform our math. So here, okay, so here is our regular math, right? This is a normal case. We can just subtract the hours and multiply that by 4 and add it to our answer. Then subtract the minutes, divide by 15, and add it to our answer, and return that. This checks the case we have described earlier, where start time is like 20 and end time is 6. So we'll need to first go from 20 to 24, and then go from 0 to 6. So this is the statement that handles that case. So this checks if start time is after finish time, in which case we know we will have to use this carryover technique. So this calculates how many rounds will go by with the minute, and this calculates how many rounds will go by with the hour. So if you just notice here, we will calculate the minutes here by doing 60 minus the minutes of our start time and dividing that by 15. So this will just give us how many rounds will go by in the minutes. Then we will do the same thing with the hour and set both to 0. So yeah, so that will just allow us to calculate the answer, and as you can see, this gets accepted. So the important realization here with this problem is you can just mathematically figure out how many rounds are played in an O of 1 time, and don't need to worry about any looping. Now let's go over the third problem, count sub-islands. Let me just clear this canvas here. And so in this problem, you are given two matrices, grid 1 and grid 2. An island is just a group of ones. So in this example, grid 1 would have this island up here with these ones, this island in the left corner that looks kind of like an L, and this group of 2 in the bottom right corner. Those are all islands. Next, we're given another grid that looks different, and we're supposed to count how many sub-islands there are. A sub-island is when an island in grid 2 lies within an island in grid 1. So as you can see, this weird shape here lies within this bigger shape here. As you can see, this is just the same shape, but with an extra 1 here instead of a 0. Because this island in grid 2 lies within this island of grid 1, this is a sub-island. We will perform this procedure for all islands in grid 2. So this island here will be a sub-island of this island here, and this island here will also be a sub-island of this island here. But these islands here are not contained within an island in grid 1, so they are not sub-islands. So because we found 3 sub-islands, we will output 3. So in this problem, it's just a simple application of DFS, or really any flood filling algorithm that you want to implement. The way I did it is I first found all the islands in grid 1. So the way you can find an island, let's just go over this first, is fairly straightforward. You can keep track of which squares you have visited in, let's just say, a helper array. Initially, none of these will be visited. Whenever we find a square that's part of an island, so we find a 1 inside of our main grid, we can simply just keep on expanding it, and that will find our island. So what that will look like is like so. So let's just say we found this. We know we have not visited yet, so we will add a marker here saying that we visited this part of the island. Next, we will try to grow in each direction. So whatever islands that we add, we know we want to explore from then. So we'll just have a stack representing the the coordinates of the next areas we need to visit. So in this case, we'll push these coordinates here. So we'll know we want to visit this one. We have that in our stack. Then we will pop it off and visit this and perform the same operation. Let's just say we have another one here. When we visit this node here, we will add both this and this into our stack of areas to visit. And whenever we visit a node, we will check mark it off. So when we visit another node, we will not keep on adding this and add this and be stuck in an infinite loop. We will only add a new node to our stack of nodes to explore if we have not seen it before. So when we process this node, we will look on all four sides. We see this node has already been visited. We see this node is a 1, so this is part of the island. It has not been visited yet, so we'll push this node into the stack of nodes to visit. We will do the same with this, and we will need to visit both of these. Using this, we can discover an entire group of islands. So what I did was I just found these islands in grid 1 and labeled them with an ID. So instead of using this check mark here, I will just add some extra information in this check mark. So I will just write an ID here. So a grid square that's not part of an island will just be -1, and otherwise it will be an ID. So let's just say there's an island here in our grid 1. Then these will have an ID of 1. And let's just say there's an island down here, so these will have an ID of 2. This represents these belong to the same island, island number 1, and this island, all these nodes in the categorized in this island belong to island number 2. Next, we can use the same thing in grid 2 to find an island. And the only difference is when we are exploring in grid 2, we need to check if the island we found is contained in a sub-island of grid 1. Because we labeled which ID each island belongs to in grid 1, we can simply check if every square we add in grid 2 belongs to the same ID of island in grid 1. So what that looks like is something like this. Let's just say in grid 2 you found an island here. Grid 1 would look like this. It is important to note grid 1 and 2 have the same exact size. So grid 1 would look like this. Let's just say both of these islands here have an ID of 2. So when we find grid 2, we know this is a start of an island. We just need to check if every single thing inside of this island in grid 2 belongs to the same ID we have found using our code earlier. In this case, we will use the same DFS algorithm starting from this node and explore this one. And yeah, and since we discovered both of them belong in the island of ID number 2 in the G1, where we calculate the IDs of each island, we know that this island is a sub-island. On the other hand, if we have a node out here, we will end up exploring this node, but discover that there is no island here. So this island will not be a sub-island of grid 1. So let's take a look at how that's implemented. So my code is very messy and very long, but I would just break it down in a very easy manner. We will first make this a new int array called G1, and this will just hold the IDs of each island. So we will go through every index in we will fill it with -1 to symbolize that we haven't visited any nodes, and we'll start our ID at an arbitrary number. It doesn't really matter. Then we will go through every index inside of grid 1, and if we have not visited it yet, and this is a start of an island, we will find that island and place the ID in our helper array that we're going to calculate. So this will just use DFS and recursively visit ones that are adjacent. So it will visit this, but it will not visit something already visited, since it checks for here. So it'll just check if this is still -1. That means we haven't visited it. So yeah, this is just repeated across each direction. Next, what we will do is we will have a new array that will help us explore grid 2. So I realized I can't just use this function for grid 2, so I manually wrote a recursive version of that with utilizing a stack. So what I will do is I will push 2 integers in the stack representing the row and column we want to explore. And we will have an integer keeping track of if this, a Boolean keeping track of if this island we have found, this is a part of an island that we have not explored, same logic as up here. So when we find part of an island that we have not already explored, we will pretend like it is a sub-island. And then we will initialize this as the island ID of this spot in area 1. So if we find an island here, we know we are looking for an ID of 2. So check will equal 2, because that's the ID. While we have more coordinates to explore, we will pop off the row and the column. Because we push in the column second, we would need to pop it first. Next, what we will do is we will say that we will this just says, yes, we explored this part of the island already. So we will not go back to it because we set, we will not go back to it here because this makes sure that that's -1, but since we set this to just an arbitrary number, we know it is not -1. So we won't go back and visit islands, part of islands that we have already visited. This just checks if the everything belongs to the same sub-island, belongs to the same bigger island in G1. So if this has a different ID than check, or if it is -1, so there's -1 means there's no island here, or if let's just say we have a 3 here and this extends out in grid 2, we know that these are part of 2 different islands, so we will also return false. So if the island ID is different than the one we found initially, or if there's no island there, we will just say that it is not a sub-island. This uses the same code here, basically saying if we can explore in this direction and this direction the node is still part of this island, we want to visit that. So this just checks each direction. If we go down, up, left, right, this checks that it is a valid index. This checks if it is part of the same island. This checks if we have not visited it already. We will push this row and column into our things to visit. And after we have visited every node in this island in grid 2, we will just need to check if it is a sub-island. So if the sub-island is still true, we will add 1 to our answer. And I just printed out these to debug. You don't need these print line statements. We will just return our answer, the number of sub-islands. So I know you can write this a lot more concisely, but it still gets accepted. And yeah, so that's about it for problem number 3. Now let's go over problem number 4. So let me just clear out my canvas. So if you notice, I actually did not solve problem number 4 in the contest, even though it was just a medium problem. I'll explain why after introducing the problem. So in this problem, you are given an integer array, and a minimum absolute difference of an array is simply just the two closest numbers that are not equal subtracted. So, for example, in this one, we see that 2 and 3 have a difference of 1. So this minimum absolute difference will be 1. It is not 0 because the two numbers must be different. So 2 and 2, you cannot subtract those. So we know this minimum difference is 1. So if every number is the same, then it's -1. So we are given an array and a bunch of queries we need to answer. The queries give a range inside of our array from left to right. We want to compute the minimum absolute difference of the subarray nums from left to right, which contains the elements from left and right. So we need to return an answer array where each part of the answer is answering the ith query. So if we just quickly look at their example here, we have a bunch of queries, and our answer will represent the minimum, minimum absolute difference of the sub array of the query. So querying the sub array from 0 to 1, that's 1 and 3 here, we will return the minimum absolute difference would just be 1 minus 3. And looking at a more complicated example, a sub array from let's just say 0 to 5 would just be all the numbers here, because this is index 0, this is index 5. And we know that the minimum absolute difference would be 4 and 5 with a difference of 1 between them, since they had the closest numbers, right? So to solve this problem, you actually need to pay very careful attention to a constraint, which is that each number can only range between 1 and 100. So when I was solving this problem, I went through pretty much two incorrect ideas. So first, I spent about 10 minutes trying to figure out if I can use a segmented tree to help solve this problem, because segmented trees are very useful for answering range queries from left to right. However, because of the nature of this problem, I couldn't figure out a way to make use of a segmented tree here, because segmented trees are really useful for aggregates, like a maximum or minimum between a range, but they are not so good for this specific situation, because if we have a range from like 0 to 1 and a range from like 2 to 3, we cannot use any information from these ranges to calculate the minimum absolute difference. So let's just say this is 1 and 100. So the minimum absolute difference we'd store is 99 in this part of the segmented tree, and this is the same two values. Let's just say like that. Let's just say they're slightly different. So 99 and 1. So then we'll store 98 in this part of the segmented tree. But if we want to find the interval from 1 and 2, we should answer 1. But there's no way to figure out that we should answer 1 just from knowing that there's a 99 difference between these two numbers and a 90 difference between these two numbers. So I don't think you can use a segmented tree for this specific problem. So then the other one I did was I just couldn't think of anything. So I just tried using a brute force solution, but obviously it times out. So now let's go into the actual solution. So the key thing here is to realize that each number can only be between 1 and 100. So the incorrect brute force solution is if you are given an array of left and right. First of all, we need to realize that to find the minimum absolute difference, we need to take advantage of a sorted array. So if we have like 1, 5, 4, 2, or something like that, it'd be easiest if we just had these all sorted. So then when we compare a number, we can just compare the difference between these two numbers, difference between these two numbers, and the difference between these two numbers. Because they are all sorted, we know we only need to compare a number with its neighbor. So there would be a difference of 1 here, 2 here, difference of 1 between these two. So we know the minimum absolute difference would be a difference of 1. So that is the first important thing to realize here. So the incorrect brute force solution is if you're given left as like 0 and right as 5, you might think that you need to just take the subarray from 0 to 5. So it doesn't matter. So like 5 elements here, sort them, and then just perform this check where we compare the neighbors. I tried this because I couldn't think of anything else, because I did not pay attention to this constraint here. And this doesn't work because, and you can tell that because there are 2 times 10 to the 4 queries. So we need to solve each query in constant or logarithmic time. This, doing this will have an n in the runtime, because when we take a subarray, this subarray could be as long as n. So we are essentially running into an n squared runtime. And this solution fails about on the 50th test case. So what we can actually do is we can take advantage of the fact that each number can only be between 1 and 100. So instead of taking the subarray of what could be like 1,000 elements, we just need to check if we just need to loop from 1 to 100 for 1 to 100. We just need to check if this number exists. So instead of this subarray, we need to check if 1 exists, 2 exists, 3 exists, 4 exists, and so on. This is much better than taking a subarray of 1,000 elements and sorting it, because this is essentially a constant time operation. Every time we're just performing a loop from 1 to 100 and checking if the subarray contains that. Then we'll essentially already have a sorted array where, let's say it contains 1, it doesn't contain 2, but it contains 3, 5, 6, whatever numbers it might contain. Now we have our sorted array, but instead of taking a subarray of 1,000 elements, we have just checked if 1, 2, 3, 4 exists in this array. So every single time when we generate our sorted array here, we will just this loop from 1 to 100 is just a constant time operation every time it performs 100 iterations, and that is much more efficient than taking 1,000 elements every time and sorting them. So now comes the question of how can we quickly tell if a number exists within a subarray of the array, and we can just use that we can solve that by doing a prefix sum. So we can have an array that keeps track of how many of each number we have seen from 0 to an index. So that can be 1 all the way to n, right? So what our array will look like is it'll have 2 numbers you can plug in. This is the ending index, so you can plug in anything from 0 to n into this, and this is the number that you want to check. So you can plug in anything from 1 to 100. So when you plug in 2 numbers, I and j, this array that we will calculate will return how many occurrences of j are within the interval from 0 to I. Now we can instantly tell if a number is within a subarray. What we can do is we can plug in the right endpoint and left endpoint. So let's just say we know there are 6 occurrences of the number 50 between sorry, not 6 occurrences. Let's just say the right endpoint is 6. So we know we want to go from a left endpoint to the endpoint of 6, and we want to check how many occurrences of 50 there are. Let's just say there are 3 occurrences. That means there are 3 occurrences of 50 between the indexes of 0 and the indexes of 6. So we'll have a bunch of 50s here, right? Whatever it may be. Now we know our left endpoint, let's just say, is 4. So we will check how many occurrences of 50 there are here. If this equals 3, we know that between 0 and 4, there are also 3 50s. So that means there are no 50s between 4 and 6, because from 0 to 6, we know there are 3 50s, and from 0 to 4, there are 3 50s. So there are no new 50s between the interval 4 through 6. So what we can do is just take the number in the right interval, subtract the number in the left interval, and if that number is greater than 1, we know that there has to be a 50 somewhere in between this interval, because from 0 to the left interval, there are less 50s than there are from the 0 to the right interval, right? So by using this prefix sum here, we can simply check to see how many occurrences of a number we have uh, between this interval, and if it is greater than 0, we know that number exists. So essentially what we can do now is we can calculate this sorted array in between an interval in just O of n time. Because we don't need to, our checking does not depend on the length of the array, we simply check all the numbers from 1 to 100, and we can figure out this if a number exists in constant time using this prefix sum. This operation to check if a number exists between an interval is just constant time. So we can generate this array in constant time by checking if 1 exists in the subarray, then 2, then 3, etc., and building this array. Then we can simply just basically loop through this, which is at most 100. So looping through is also a constant time operation, and just compare the neighbors and find the closest pair of neighbors. So now let's take a look at how that's implemented. So we will initialize an array here that will help us use our prefix sum. And as you can see, plugging in two numbers here, we know we can plug in numbers from 1 to 100 for j, and we can plug in any number within our range of nums. So as you can see in this comment, this is the number of occurrences of j between 0 and I of our nums array. This calculates the prefix sum and puts all our information into count. We do this by, we can first add 1 to the 0th number in nums. So this means that between 0 and index 0, we will have 1 occurrence of this number. Then what we can do is we can start from 1, check every number from 1 to 100. We will copy over that value from previously and add 1 to the number that we currently see. So this will calculate this entire prefix sum basically, because for every number, we know that the number of occurrences from 0 to I would be of j, of the jth, of j, which j is between 1 and 100. We know that it is the same as how many occurrences there were previously, and then we just need to add 1 to the number that we currently see because it occurs 1 more time than its previous amount. So this will calculate our prefix sum. Next, we will just find our answers. So we will make a new answer array, which we want to return. We will go through every query here. So Q will be the ith query. And then we will simply check if each number occurs in the interval from the left endpoint to the right endpoint. So this here essentially just calculates the number of occurrences. So this math here is our regular math. So regularly what we want to do is we want to take how many occurrences of the number we have. So because our prefix sum is inclusive, right, you can do this in multiple different ways, but this is just the way I implemented it. So from 0 to let's just say index 5, that's our right endpoint, we'll want to know how many numbers occur. Then if our left endpoint is 3, we'll want to know how many numbers occur from 0 to 2, and then we know we can just subtract the right prefix sum, which will include these numbers, which is our interval, and this one to figure out if there are any new occurrences of a number within this interval. But the only issue is when our left endpoint is 3, we can easily subtract 1 and just find our prefix sum of 2. But when our left endpoint is 0, we can't just have a -1 in our prefix sum. So we just need to set this imaginary sum here to 0. So if the left endpoint is at 0, we just take how many occurrences of j is within our interval just from 0 to the right endpoint. Otherwise, we subtract 1 from the left endpoint and use our right endpoint as normal. And this is the number of occurrences of j between the left and right number in this interval. If there are an occurrences, we will basically, we know that 1 will occur in this array. So basically, I'm just taking a shortcut. So what you can do is you can check if each number occurs, shove them into an array. Let's just say 1, 3, 4, 5 occurs. We find these 4 numbers occurs, shove them into an array, and then compare neighbors. I'm just combining these steps into one. So I have a previous value here. So basically, if we have seen a previous value, we know that that previous value will be a neighbor of j. So we can just simply do our comparison right here. So this minimum gap will just be the minimum previously and the difference between these two neighbors. And then we set the previous guy to j. So instead of putting everything to an array and comparing the neighbors, we'll just have a running track of which is the previous number. So if our previous number that we found is 3, we check a bunch of numbers, we eventually find that 7 is the next number that exists. We know 7 and 3 are neighbors, so we can just check them. They will have a difference of 4. So then we can just check it, and yeah, so this combines the 2 steps into one, and we will just return, we will just put our answer into our answer, right? Because then this minimum will represent the closest two numbers that we find. Since we started off at max value, if it is still equal to the max value, we will make it -1, and otherwise it will be the minimum. And essentially what this will calculate is because we check each unique number from 1 to 100, basically if all the numbers are the same, we will never have a previous that is not equal to 0, so our minimum will remain at the maximum value. And this is important because the two numbers must be different, as you see here. So since we're checking different numbers here, if there are multiple the same number, we'll know that this entire interval of the array will all be comprised of the same number. So if it is still equal to the max value, that means that in our sorted array we generate here, there will only be one, or yeah, so there will only be one number here, so 3, whatever, because only one number will exist in that interval. So if only one number exists in that interval, all the numbers in the interval are the same, we will return -1. Otherwise, we will just return the minimum, and we'll put that in our answer. After we answer all the queries, we will return the answer. And if we submit this, we can see that it gets accepted, and this is pretty much the bare minimum for you to get accepted. Yeah, so the reason why this gets accepted is because if you take a sub-interval of, let's say, 1,000 elements, that will have an order of n in the runtime. So let's just say we know there are 10 to the 4 queries, so let's just say m is number of queries, and n is the length of nums. So there will be some sort of m times n in our runtime if we have to sort a sub-array of n every single time. But in this case, because we are not sorting a sub-array of n, we are simply taking advantage of the fact that there are only 100 numbers to check. We check if these 100 numbers exist. So this is just m times 100, and that's a constant. So our runtime will actually be O of m, because figuring out if the answer to a query will essentially just be in constant time. This is just checking for each number if it exists. So this way, we will avoid having a m times n order of runtime in our answer. Because m is quite large and n is also 10 to the 5, if we multiply them together, it will simply time limit exceeded, and that it will not get accepted as an answer. So yeah, and calculating this prefix sum will also be in constant time, because this is 100, multiply that by the length of nums, that's still constant time. So yeah, so this will essentially run in constant time. So yeah, that's the reason why it will get accepted. So yeah, I wasn't able to figure out this during the contest. I failed to take advantage of this restriction on numbers, but in the future, it is just an important takeaway here that when when you have an array with a lot of numbers in it, but the numbers are restricted to a very tight range, instead of taking all the numbers inside of this array, we might be able to just check if each number inside of our range will exist. That way, we'll be a lot more efficient. So that's just an important takeaway that I have after this competition. And yeah, so that's about it. These are the solutions to problems 1 through 4 of weekly contest 246. I will provide source code in the description. Thank you very much for watching, and I hope you enjoyed the video.